Dear classmates, welcome back to the fault simulation chapter. In previous video, we have shown many fault simulation techniques, and we know that fault simulation is slow. So in this video, we are going to introduce some alternatives to replace fault simulation. This video includes toggle coverage, fault sampling, and critical path tracing. Imagine this scenario. Suppose that your boss asks you, why can we speed up the design sign-off? And you told your boss that fault simulation is very slow. And your boss said, we do not need exact fault coverage at this stage of the design. Just give me an estimation and do it fast. So what should you do? This is a good question. Is exact fault simulation necessary? Sometimes we don't even have to know the exact fault coverage. We just want to know approximate fault coverage with reasonable error. So this is the reason why sometimes we need alternatives to fault simulation. Approximate fault coverage is good for DFT check in early design phase or functional test pattern evaluation. Sometimes we just want to know approximately how good our test patterns are. We don't need to know the exact number. But please know that approximate fault coverage is not good for ATPG. It's not good for diagnosis, because for ATPG and diagnosis, we need to know exactly which pattern detect which fault. Okay, so let's start with the first alternative, toggle coverage. The definition of toggle coverage is shown in this rectangle. In the denominator, we have 2 times the total number of faults. This pound sign represents numbers. In the numerator, we have a summation of the number of different values of every node in the circuit. For example, given this circuit, we have A, B, C, L, E, F, H, J, K. Totally, there are 9 nodes in this circuit. And for node A, we have 2 values. For B, we have 0 and 1. So also we have 2 different values. C is 2, E, F, L. But for H, we only have 1 value, which is 0. For J, we have 2, and K, we have 2. So totally, we have 17 different values. So if we apply these 3 test patterns to this circuit, we would have 17 over 18, which is approximately 94.4% toggle coverage. So the advantage of toggle coverage is that toggle coverage is easy to obtain. We only need logic simulation. We don't even need fault simulation. So this is very simple to obtain. But the problem of toggle coverage is that it's very optimistic, because in toggle coverage, we only care about fault activation. We don't even care about fault propagation. For example, for signal L, we only know that it has been activated to 1 and it has been activated to 0. But we don't know if they are propagated to the primary output or not. So we can say that toggle coverage is an upper bound of fault coverage. For example, for this circuit, the fault coverage is 61% only, but our toggle coverage is 94%. So in this case, we can see that toggle coverage is too much larger than the fault coverage. If you want to know the detail of fault coverage, you can review the video 5.3 on page 10. So now, it's time for you to work on a quiz. For this circuit, suppose we apply 3 patterns, and we have 7 nodes in this circuit. Please tell me the toggle coverage. Okay, have you done yet? This should be pretty easy. The value of each node can be filled in, and the toggle coverage is, we have 13 different values. Every node has 2 different values except output C. So in the numerator it's 13. So it is approximately 92.8%. Have you got it correctly? Now, some people have different definition for toggle coverage. They think toggle means that a 0 to 1 rising transition and 1 to 0 falling transition. By this definition, then we would need to change the numerator a little bit. By this definition, we need a total number of different transitions of every node in the circuit. The denominator is the same as our previous definition. So, given this same circuit and the same patterns, we can calculate the toggle coverage again. For node A, we have a 0 to 1 rising transition. For B, we have 1 to 0 falling transition. For C, we have a rising transition followed by a falling transition. So we have falling, 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 and no transition here. And we have rising and falling. So by this definition, the toggle coverage would be 9 transition over 18. So the toggle coverage is only 50%. So we can see that definition 2 is more stringent than the previous definition 1. Now let's move on to the second alternative, fault sampling, which was proposed in 1974. The idea of fault sampling is actually very simple. The fault simulation of the whole circuit is too slow. Can we just sample a small portion of the fault so that we can speed up the fault simulation? It's just like polling before a real election. Suppose this big pie chart represents the total population, and this small pie chart represents a small portion of the total population. We can just run fault simulation on this small number of sampled faults so that we can estimate our fault coverage. So, suppose that big M represents the number of total faults. That is the size of the total population. And the small m represents the number of sampled faults. That means the size of this small sample pie chart. Suppose that big K represents the number of total faults that are detected by the test pattern. Please note that this is an unknown number. because we don't know exactly how many faults are detected in the total population. And the small k represents the number of sampled faults detected. This number can be known from our fault simulation. So, the actual fault coverage, big F, is equal to big K over big M. Because we don't know big K, so big F is unknown. On the other hand, we know the sampled fault coverage, small f, which is small k divided by small m. Now, we need some statistic to handle this concept. Suppose that pk represents the probability that a test detects small k faults from a random sample size of small m, given that it detects big K faults from big M total faults. It was derived by the paper that pk is hypergeometric distribution of discrete value, which can be written in this equation. Unfortunately, this is not very easy to handle. But the good news is that for a very large M, pk can be approximated by normal distribution of continuous value. This is a good news because we know how to handle normal distribution very well. The mean of this distribution, mu k, and the standard deviation of this distribution, sigma k, can be written in these equations. If you want to know the details, please refer to the paper. So the conclusion is that for large M, the sample fault coverage small f is a random variable with normal distribution where the mean is actually f. From this figure, we show the probability density function PDF of the sample fault coverage. In the middle is the mean, mu f, which is the actual fault coverage, big F. And the standard deviation, sigma f, is equal to this, which can be approximated by square root f times 1 minus f divided by small m. Suppose that in our fault simulation we obtain a number here. Then the distance between the real fault coverage and our simulation fault coverage is called the sampling error. So how much confidence do we have in our prediction? So confidence level means the probability that our estimated fault coverage, small f, falls in between the confidence interval. For example, we can use plus and minus 1 sigma f as our confidence interval. That means the probability that our simulation fault coverage falls in this area is 68.27% of the total area. If we increase our confidence level to plus and minus 2 sigma f, then our confidence level would increase to 95.44. The most useful confidence level is plus and minus 3 sigma f. In this case, our confidence level would increase to 99.73%, which is good enough for many cases. So now let's show you an example. Suppose that in our circuit there are 1 million total faults, and we sample only 10,000 of them, which is 1% of big M. Suppose that in our fault simulation, we know that the fault coverage is 70%. So we can plug in this number to the equation, and we have 0.7 times 1 minus 0.7 divided by 10,000, which is equal to 0.005. So we know that the standard deviation is 0.5%. Please note that big F is a known, so we use the mean as the big F. If we want 68% confidence level, we can use only plus and minus 1 sigma F. If we want 95%, then it's plus and minus 2 sigma F. If we want 99% confidence level, then we need plus and minus 3 sigma F. Similarly, this column shows the case where the fault coverage 80% and the 90% and the 95%. We can see that sigma F decreases as the fault coverage increases. This is quite intuitive because when the fault simulation result is good, we have some more confidence. So in conclusion, from this table, we can see that an accurate prediction means that our confidence level is high and the confidence interval is small. Now, let's work on the previous example. Suppose the fault coverage is 95%, but now we want to increase our standard deviation sigma F to 0.1%. In this case, how many samples do we need? So what's the value of small m? Please pause the video and do the calculation. Okay, are you done yet? From this equation, we can know that sigma F squared is equal to F times 1 minus F divided by M. So we can know that M is equal to F 1 minus F divided by sigma squared. If we plug in the number, we can see that this is 0.95, this is 0.05 divided by 0.001 squared. So the answer should be 47,500. Have you got it correctly? Now let's move on to the third technique, critical path tracing, which was proposed in 1979. A signal X is critical if X value change cause some primary output values to change. For example, suppose this simple circuit has one AND gate. The primary output 1 is of course a critical signal, since any change in the primary output can be directly observed. So the critical signal is circled in this example. For these two gate inputs, they are both critical signals because they are non-controlling values. If this one is flipped to 0, the output would also be flipped to 0. So this is of course a critical signal. And similar things here. For the second case, the primary output 0 is critical and the 0 gate input is critical. If this is flipped to 1, the output will be flipped to 1. However, the 1 gate input is non-critical. Since this is non-controlling value, if we flip this 1, the output still remains 0. So this is not a critical signal. Now for the third case, the primary output 0 is critical, but neither of these two gate input is critical. Because 0 is a controlling value, even if we flip 1, 0, the output won't be changed. So both zeros are non-critical. And we define that a critical path means that all signals on this path are critical signals. So the critical paths are highlighted in blue lines. Please note that in timing analysis, critical path has a different definition. In timing analysis, a critical path means a path with the longest path delay. This slide shows the critical path tracing algorithm. This algorithm recursively traces the critical path, starting from the primary output to the primary input. If the gate output is critical, then we backtrace its critical gate input. For example, the following shows a Fanout-free cone, FFC. In this circuit, it does not have any fanout, so we call it a Fanout-free cone or Fanout-free circuit. Suppose that G is a primary output, so of course G is critical. Then we trace its critical gate input. This one is a critical signal, and for this AND gate, both A and B are critical signals. So we have 4 critical signals, A, B, F, G, and we have 2 critical paths, A, F, G, and B, F, G. This is not critical, since if we flip this to 1, the output won't be changed. So this is non-critical. So we don't have to trace along this non-critical signal. So here is the CPT algorithm. Given a circuit node O, for each gate input G of O, if G is a critical signal, then we recursively perform the CPT on G. This is finished until we hit the primary input, and then we finish this CPT algorithm. We can see that this is a very simple algorithm that can be finished in linear time. Now, we introduce the CPT theorem. If a critical signal G has good value V, then G stuck at V fault is detected by this pattern. This is a very simple and straightforward theorem. Given this same circuit and the same pattern, we can say that A stuck at 0,4 is detected. If we flip the value of A, since it is a critical signal, the output will be changed to 0. Similarly, B stuck at 0,4 is detected, F stuck at 0,4, and G stuck at 0,4. They are detected. So this test pattern detects 4 stuck at 4. We can easily determine the number of detected 4 by this test pattern. So the CPT has many advantages. It can be done in linear time. We only need logic simulation for Fanout-free cones. So this is actually used in the first commercial ATPG tool, laser. CPT is very fast. However, it has one limitation. Can we determine the criticality of Fanout Stem? For this example circuit, we apply test pattern 110. The output K equal to 0 is of course critical signal, and the H is a critical signal. L is also a critical signal. However, F is not a critical signal. So how can we determine the criticality of Fanout Stem E? Suppose we flip the value of E to 0, and this would be flipped, this would be flipped, this would be flipped. J is also flipped. So we can see that K is not changed. So we know that E is actually non-critical. So is this always the case? I mean, Fanout stems are always non-critical. Can we prove that? Now it's time for you to work on this quiz. Please now pause the video and work on this problem. You will find the answer. Are you done? Suppose we apply 0, 0, 0 to the same circuit as the previous page. We can run a logic simulation and obtain the good values. So of course K is critical. H is not critical, so we will not continue to trace its gate inputs. In this case, J is critical, so F is critical. Now we want to determine the criticality of Fanout Stem E. Is E critical or not? Let's try to flip the value. We can see that J is flipped to 0, so K would be flipped to 1. So in this example, Fanout Stem E is critical. So the result of this quiz is opposite to our previous example. So actually we don't know how to determine the criticality of a Fanout stem unless we perform a real fault simulation. So critical path tracing actually does not work well when Fanout reconverge happens, like in this example. So what should we do? Since there are many fan-outs in a circuit, we have two simple solutions. Solution number one, we can count Fanout stem as non-critical. This is a fast solution, but the fault coverage can be pessimistic. Solution number two, we can perform fault simulation only on Fanout stems, and then we perform CPT inside the Fanout free cones. For example, in this circuit, the blue lines represent Fanout stem. We can perform fault simulation on the Fanout stems, and the triangle represents Fanout free cone. We can perform CPT inside this Fanout free cone. Of course, this solution is slower than solution number one, but the fault coverage can be more accurate. So now, in summary, in this video we have shown three alternatives to fault simulation. They are fast, but they may not produce accurate results. The toggle coverage is very simple. It can be obtained by logic simulation, and there are two different definitions of toggle. Fault sampling only fault simulate a small portion of the fault, and we can determine the confidence level and the confidence interval based on statistical method. Critical path tracing is a linear time algorithm for fan-out free circuit, but we still need fault simulation when fan-out reconverges. Finally, we have two interesting FFT for you to think about. Question number 1. For CPT, actually there are 4 cases. For example, when one fan-out branch is critical, the stem can be non-critical. When one of the fan-out branch is critical, the fan-out stem can be critical. We have already shown these 2 examples in this video. So now it's your turn to show me these other cases. When both fan-out branches are critical, the stem is non-critical. And there are also cases when both fan-out branches are non-critical, but the fan-out stem is critical. Please give me example circuit and test patterns. Question number 2. In this video, we mentioned that toggle coverage is greater or equal to fault coverage. Can you prove this? These are 2 interesting questions for you to think about. Thank you for watching the video.